2.3, asymptotic notations. Finally, we need to go to abstract math. This topic is very abstract, but very important. For algorithm analysis, we need to do this. Very important. But understanding is not easy, very abstract. Okay. Recall that we use limits to compare two growth functions. We just did it, so let's look at that problem or that computation again. Yeah, but this time we look at the general limit. F function over G function, general function. Because we want to use a general theory to describe which growth function is faster, which growth function is slower. General theory of it. All right. If we look at this limit expression, how many possibilities do we have? In general, when we work on this calculation, how many possibilities do we have in general? So can you see that? 4 cases. Here I'll give you 4 cases, okay, to cover all the possibilities. The first case, the limit is 0. That's possible, right? Okay. The second case, the limit is a non-zero constant, C. C, non-zero constant, some constant. Okay? Yeah. The third, infinity. Also possible, right? But there is last possibility, none of the 3. Can you imagine? The limit could be none of the 3. Can you imagine that? Is that possible? Negative? Oh, negative infinity. Oh, negative, I'm putting this in. Okay. Because negative, positive, not that important. Now we can take absolute value if we need. Now that's, fundamentally different. Okay. So there is a possibility not in any of the 3 cases. The limit does not exist. There is no limit. The limit does not exist. Not infinity, not 0, not any non-zero constant. It just does not exist.
You're just saying that there's a hole in it? It's a non-linear.
There is a hole. All right. It's hard to imagine, right? It's hard, yeah, because at this point, it's not easy to imagine it. So let me show you a simple example, so you will get convinced. Let me show you a very simple example. All right, let's see this limit. Is that good? Okay. Numerator. How about this? Is this good? -1 to the nth power times n, okay? Denominator n. What is this limit? What is this limit? Okay. We can do cancellation, right? So n cancel out. What's that limit? +1, -1, +1, -1. When you see that, is there a limit? No limit. Yeah? The limit does not exist. Okay? This case, can we put in the other? Because that means it's not 0. It is not infinity. It is not a non-zero constant C. So we put in other case. Does not exist. That's a simple example. All right. Let's keep going. Yeah. All right. Zero case. When we see the zero case, then we can say the order of growth of f of n less than order of growth of g of n. Now, when we comparison, the numerator, limit approaches to zero, we can safely say, that number, that limit is less than a fraction of a small fraction, right? 1/10, definitely. Something approaches close to zero is less than 1/10, right? So definitely we can say the bottom function has larger order of growth than the top function, that of the top function, right? Yeah. So that's the first case. Second one, we can say they have the same order. Non-zero constant. Same order. We can say that. Okay. Limit of infinity, we can say the order of f of n, order of growth of f of n, greater than order of growth of g of n. How about the other case? The limit does not exist. Anything is possible, right? Any of the three is possible, but we don't know. We need more information. We don't know. So we need to do more work for this case. Yeah. So our following discussion, we will work on the other case. Yeah. Although sometimes we also discuss the first three cases. Now we use asymptotic notations for the first three cases. That's the relatively easy part. Case one corresponds to this limit zero case. We use a shorter, simpler notation. Yeah, because we don't want every time we write long sentence, right? So that's not efficient. We don't want every time we write long sentence to represent this meaning. Okay? We want a short notation to represent the same meaning. Okay? Shortman f belongs to little o of g of n. Little o. Okay? This is asymptotic notation. Okay? This is a set of functions. This notation means a set of functions. All the functions in this set of functions has this property. Order of growth less than that of g. Okay? So we put all those functions in one set. So x is an element of that set. That's the meaning. All right, for the case number two, the notation is big theta. Asymptotic notation, this time we use big theta to represent the set. The same orders, we use big theta. All right, the third case, we use little omega. Little omega. Okay? Here you can see if we use these three cases, we can save a lot of words. We do not need to write those long sentences. Okay? We can write shorter notations like that. But just do not get confused. Okay? Which notation, which asymptotic notation corresponds to which case? Do not get confused. All right. Next, we need to go to the other case, the harder one. This time we will, because the limit cannot tell us anything. Limit does not exist. We cannot use limit for this situation, we have to use a different way to tell us useful information. What method? Using upper bounds and lower bounds to tell us more information this time. Okay? Even the limit does not exist, but we can still find upper bounds or lower bounds. Okay? So now, let's focus on the case this limit does not exist. Analysis. Usually, because when we compare the growth functions, two growth functions, usually we like to choose g function as relatively simple functions. N squared, n log n. F of n usually could be a complex function. So that's the way we use in real world analysis. But how do we use a simpler function to describe a more complex function? We use some constant multiple of a simpler function to approximate a complex function. That's the way. Because the constant multiple of a simple function, we have an idea how fast, how large it is. Yeah? C, constant C times n squared. We have some idea, right? We have some idea. But for complex function, we don't have an idea. So that's why we want to use constant multiple of a simpler function g of n, to estimate a complex function f of n. Specifically, can we find two positive constants C1, C2 such that we have this inequality? So you can see, because our goal, we want to estimate f function. Okay? Now, the way we want to estimate from lower bound side and from upper bound side, two sides, so we can get a better description. Two sides to estimate that function. Here you can see, here we do not require that the limit exists or not. Even the limit does not exist, we can get a lower bound function, upper bound function. Okay? All right. So this method works no matter the limit exists or not. All right. So using this method, now try to find the relationship between two growth functions. All right. But with this looks a better method, right? Yeah, because more robust, right? But it does not mean the old limit method is not useful. The old limit method is still useful. Okay? Because when the limit of that ratio exists, that is still a powerful method. When the limit exists, this method is powerful. Okay? Because you can take the L'Hopital's rule. Many powerful techniques you can use. But in this case, upper bound, lower bound, can you use L'Hopital's rule? No, you cannot use L'Hopital's rule. Okay? So that's why sometimes not very easy to estimate in this way. Okay? So that all the methods we use for the limit still useful for us. Okay? Don't throw away. All right. Big O notation. Now let's try to look at its definition. Big O notation. Definition. for a given function g of n, it's a known function. Usually, when we choose a simple function. The notation big O of g of n, big O, not little o. Remember we saw little o before, but this time it's a big O. Represents the set of functions f of n that satisfy the following condition, upper bound condition. Okay? There is one sentence before that condition. Yeah. There exists some positive constant c and some negative, non-negative integer n0, okay? And such that f of n less than or equal to c times g of n for all n greater or equal to n sub 0. What's that? What's that? Usually we say this one. Usually for this condition, when we say when n is sufficiently large, you can frequently say when n is sufficiently large. But what's the meaning of n sufficiently large? Because this n0, you can choose any number. You have freedom to choose any number for this n0, but after you select it, it must be fixed. You can choose it. As soon as you choose it, fix it. When n changes, we always use the same n0. When n greater or equal to n, you can choose any n greater or equal to n0. So why we have this n0 thing in our big O notation? The reason is very simple. So let me explain the reason why this a sufficiently large condition. Use it. Think about it. I told you before, when we compare two algorithms, when the input size is small, the comparison is not important. When the input size is relatively small, the comparison is not important. Why? I told you, because the overhead could be a bigger factor. The overhead is big, so it distorts the relationship. Okay? So usually we don't look at the input size relatively small. Okay? So here, the role of this n0 telling us, go look. Now look at the initial part. Okay? Go far enough. Okay? Go move far enough to skip that overhead part. We don't want to look at the overhead part. Okay? So go far enough to pass that, overhead part. Then we look at the, future, where n is large, then the trend will be reflected by the, that relationship. Limit or equality, inequality, things. All right, so this is the big O notation. So the definition, very abstract, but I hope so you can understand it. We can also use a graph